Okay guys, lesson 3.4 is all about Pascal's triangle, and basically what we're going to do is be using these numbers here, which are Pascal's triangle. It actually keeps going on and on, to help us solve some expanding different levels of polynomials. So before we get into how it can help us, I want to look at how Pascal's triangle is set up. First of all, it is made up of a triangle of 3 ones. I always like to start right here. So we're going to start by recreating what's going on there. I'm going to recreate that triangle of numbers there. And I'm going to start with 3 ones. 1, 1, 1. Basically, I've made a triangle out of them. Now, beneath each set of numbers, notice there's a 1 and 1. I'm going to add those two together, and I get 2. 1 and 1 is 2. And I'm going to put a 1 on each side there. So I've got 1 plus 1 is 2, and I put 2 ones, one on the left and one on the right. I'm going to do the same thing again here. I'm going to add 1 and 2 together, and I get 3. And then I'm going to add 2 and 1 together, and I get 3. And then I am going to flank it on the left and the right with a couple of 1s there. 1 on the left, 1 on the right. I'm going to do this process again, and here I've got 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And a couple of 1s one on the left, 1 on the right. And if you can see, all these numbers are matching exactly what we have on the left. I'll add one more row. Now, we can keep going on forever and ever like this, but actually what we're going to do is just add it so it matches what we've got over there, what we have on the left-hand side. So 1 and 4 is 5. 4 and 6 is 10. 6 and 4 is 10. 4 and 1 is 5. With 1s on the left. So that's how we construct Pascal's triangle. Now we're going to talk about how we use it. So these numbers are going to help us expand binomials. So notice we've got all these binomials here, and we've got 1 to the 0 power, to the 1st power, to the 2nd power, 3rd power, 4th power, 5th power. And we're going to learn how to expand them. Now, if we didn't have this trick, what we would have to do is, well, the first one's actually pretty easy. The a plus b to the 0 power, we know that anything to the 0 power with the exception of 0 will equal 1. That one's kind of easy. And actually the second one's not too bad either. It says a plus b to the 1st power. Well, anything to the 1st power is just going to be itself. That'll end up as a plus b. But after that, it gets a little bit more difficult. For example, when we do a plus b squared, what that means is a plus b times a plus b. Now, if you were to FOIL this out, it would take some work, not a terrible amount of work, but you could FOIL it out and figure out what exactly that answered. But just as a little cheat sheet here, it's showing right here that what it would equal is a squared plus 2ab plus b squared. If you work that out, that's what you would get. Now, we'll see where this is all going in just a minute, but let's say that I had a plus b to the 3rd power. Well, that would be a plus b times a plus b times a plus b. When I multiply all those 3 things together, that's going to take even more work than the last one, but it would end up right here. I'm saying that, I'm showing this reference up here, because when we do an actual couple problems here, I want to prove that this matches up. So we've got a plus b times a plus b times a plus b times a plus b 4 different times, because this is, oh, let me clean that up a little bit. A plus b 4 times, because it's to the 4th power, multiplying that 4 times. And when we expand that, what we'll be left with is all of this over here. And finally, when we do a to the 5th power, we'd get all this. So it actually takes a lot of work to do it that way. Pascal's triangle allows us a little bit of a cheat way to do this, and that's what we're going to look at right here. So we're going to move down to a right here, and we are going to expand this. Basically, it means we're going to do a plus b times a plus b times a plus b. 3 times. But we're not going to do it the long way. We're going to use this new way. Now, when we're doing something to the 3rd power, we're going to use Pascal's triangle. So this is what Pascal's triangle looks like again. Remember, we had a triangle of 1s, 1, 1, 1. When we add 1 and 1, we get 2 with 1s on the side. I'm going to keep going, and I've got 1. 1 plus 2 is 3. 2 plus 1 is 3 with a 1 on the side. So here's what we do with Pascal's triangle. If I were trying to figure out something to the 0 power, I would use this line right there. If I were trying to figure out something that is to the 1st power, I would use that line there. If I was trying to find something to the 2nd power, I would use this line here. If I'm trying to find something to the 3rd power, I would use this line here. Well, I am trying to find something to the third power. If I needed something greater than that, like the fourth power, the fifth power, I would keep adding more lines onto Pascal's triangle because we already know how to build it. So these numbers right here are going to be very important to solving this when we expand this binomial. All right, so what we've got here is the numbers 1, 3, 3, and 1. I'm just taking those numbers from Pascal's triangle. Now, if you notice, there's an A and a B up here. So all of these numbers down here, what we're going to do is we're going to put an A on each one and a B on each one. A on each one, B on each one. A on each one, B on each one, A on one, B on one. Now, there's going to be different exponents too, so we need those as well. So here's what we're going to do. We're going to take whatever this first term is right there, and we're going to start with 3. So we've got a to the third power, and then we're going to work our way down. A to the third power, a squared, a to the first power, a to the 0 power. So notice every a there got an exponent. Now, I'm going to put exponents on b as well, but with b, I'm going to start at 0 and work my way up. Before, for the first term, I started at 3 and worked my way down. Now I'm going to start at 0 and work my way up. 0, 1, 2, 3. Now we're very close to the end. We just need to actually figure out, well, what does each one of these equal? So we're going to look at this first one here. So we've got 1 times a to the third power times b to the 0 power. Now we have to remember that b to the 0 power is the exact same thing as 1. So we get 1 times a to the third power times 1. Well, 1 times a to the third power is a to the third power times 1 is a to the third power. Moving on to the next term. We've got 3 times a squared times b to the first power, which we can just write as b because that's b to the first power, which would just be 3a squared b. There's our second term. Next, we've got 3 times a to the first power. We can just write that as a. B to the second power, that's just b squared. So we get 3ab squared. There's our next term. Finally, our last term is 1 times a to the 0 power, which is 1, times b to the third power, b to the third power. So 1 times b to the third power, that would just be b to the third power. Now, none of these were negative. I didn't see any I didn't see any negative numbers in there, so I'm just going to add pluses in between there. If they were negatives, we'll see an example of that coming up, which means my final answer looks just like this. A to the third power plus 3a squared plus b plus 3ab squared plus b to the third power. Now notice none of those can be combined because while some of them have both a's and b's, the a's aren't to the same power and the b's aren't to the same power. They have to be exactly the same power. So this is my final answer. Now, why did we do all that stuff at the beginning? Because in the beginning, remember, we had the same a plus b cubed. And basically what it said was that this was the answer there, and we're going to just double check that. I'm going to zoom out there. So here we've got that a up here. I'm going to highlight it in red. A to the third power, 3a squared b plus 3ab squared plus b cubed. That's exactly what we got down there. So it's our way of expanding it. So you can expand these things without doing all the math. At first, it kind of seems like, well, wow, why would I do it that way? That doesn't seem like it's very fast. It is very fast. The faster you get at this by just doing it yourself. And remember, it looks like it's taking longer here because I'm explaining every step as we go. You're going to do a lot of this in your head. If I weren't explaining it, it would go much quicker. So this one I'm going to do a little bit faster here. Now again, the third power. So building my Pascal's triangle, you don't have to build it every single time if you've already gotten it written once. So here we go, 1, 1, 1. My triangle of ones. My next row is 1, 2, 1. Then I get 1, 3, 3, 1. Well, this first row is for something to the 0 power, to the first power, to the second power, and to the third power. And to the third power is exactly what I need. So I'm going to use those same numbers again. 1, 3, 3, 1. Except for this time, each one of those is not going to get an A and a B. Each one is going to get an X, and each one is going to get a 5. So X for each of them, and a 5. Oh, that's a little close there. Let me space that out. And a 5 for each of them. So remember, just like last time, I took the first term there, whatever it was, and I'm going to start with the third power. So x to the third power, then x squared, then x to the first power, then x to the 0 power. Now, for the second term there, I'm going to start at 0 and work my way up. 5 to the 0 power, 5 to the first power, 5 squared, 5 to the third power. Let's simplify. 1 times x to the third power times 5 to the 0 power, which we know is 1. So 1 times x to the third power becomes x to the third power. Moving on to our next term. 3 times x squared times 5 to the first power. Well, 5 to the first power is 5. 3 times 5 is 15, times x squared is just x squared. So second term, 15x squared. Our next term, 3 times x to the first power. Well, x to the first power is just x. And then finally, we've got 5 to the second power, which is 25. So 3 times 25, just like 3/4, that's 75 with an x attached to it, 75x. Last but not least, 1 times 5 to the third power. 5 times 5 times 5. Well, 5 times 5 is 25. And if I've got 5/4, I've got $1.25 or 125. So we end up with x to the third power plus 15x squared plus 75x plus 125. None of those terms can be combined because all of their variables are to different powers there. So we've got our final answer. Now, if you don't believe me that this is faster, go through and actually expand that there and do it manually. Do x plus 5 times x plus 5 times x plus 5. You'll still get the same answer, but you'll see it'll take you a little bit longer to do it. All right, I'm going kind of out of order here. I'm going to say B for the last one I'm going to do on this page because B, I think, takes a little bit more work because it's got a negative in there. It's no different. It just takes a little bit of different thinking there. So let's do D first. This is to the fifth power. That's a lot. That's x plus 2 5 times. But with Pascal's triangle, this should be much easier. There's my triangle of ones. 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. Now remember, I'm getting those numbers by adding the two numbers above it. Like I got the 6 by adding those two 3s above it. So this is to the 0 power, the first power, the second power, the third power, the fourth power. Well, I need a fifth power, so I'm going to need another line here. 1, 5, 10, 10, 5, 1. This is for things to the fifth power, and I'm going to use this line right here. So those are the numbers I'm going to write down. 1, 5, 10, 10, 5, 1. I'm leaving myself a little bit of spacing because I know that I need those variables attached to them. So I've got an x, each of them needs an x, and each of them is going to need a 2, a positive 2. So I'm going to give an x to each of them. Here's an x for each. X, 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 and each of them need a 2. Times 2, times 2, times 2, times 2, times 2, times 2. Now, remember the first term. Now, I'm going to start off with the fifth power and work my way down. X to the fifth power, x to the fourth, x to the third, x squared, x to the first power, x to the 0 power. I'm going to, on the positive 2, the blue numbers, I'm going to go the opposite direction. I'm going to start at 0 and work my way up. 0, 1, 2, 3, 4, 5. Go one by one, and let's simplify these. 1 times x to the fifth power times 2 to the 0, and 2 to the 0 is 1. So this becomes x to the fifth power. Here we've got 5 times x to the fourth power times 2 to the first power, which is just 2. So 5 times 2 is 10 times x to the fourth is 10x to the fourth. Now we've got 10 times x to the third times 2 to the second power, which is 4. So 4 times 10 is 40 times x to the third is 40x to the third. Next up, 10 times x squared times 2 to the third power. 2 times 2 times 2, which is 8. which will give us 10 times 8 is 80, times x squared is 80x squared. Two more. 5 times x to the first power, that's just x, times 2 to the fourth, 2 to the fourth power. 2 times 2 times 2 times 2, which will give me 16. Okay, sorry, hit the button there to stop recording, but we've got 5 times 16. 5 times 16 will give me 80, and 80 times x is just 80x. Last one we've got here is 1 times x to the 0 power. Well, x to the 0 power is 1. And then 2 to the 5th power, which is 32. So 1 times 1 times 32 gives me 32. Let's put this all together. We've got x to the 5th power plus 10x to the 4th power plus 40x to the 3rd power plus 80x squared plus 80x plus 32. Now, we would have gotten that same answer if we would have done this the long way by just sitting there doing x plus 2 times x plus 2 times x plus 2 all the way until we've done it 5 times. But why not just have a much faster way with Pascal's triangle? Now, we're going to do another one here that involves negative numbers. So this is the situation that usually people go, well, wait, why does it always end up positive? It doesn't always end up positive. It just so happens that the 3 examples we've done so far had positive numbers. So we're going to try one that does not have positive numbers. So we're going to go up to B here. Now, this is to the 4th power. So here we go. Pascal's triangle. We've got 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Okay, so our first row is for things to the 0 power. This is for things to the 1st power, for the 2nd power, for the 3rd power, and right here is our line for things to the 4th power, which is exactly what we have here. This is being raised to the 4th power. 1, 4, 6, 4, 1. So I just write those numbers down, and now I need to put an x on each one of them. Okay, so let's put an x on each one. X, 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 X. But I also need to put a negative 2y on each of them. Negative 2y. Negative 2y, negative 2y, negative 2y, negative 2y. Remember, I need to take the first term, the x, and I'm going to start off with the 4th power and work my way down. So 4th power, 3rd power, 2nd power, 1st power, 0 power. Now with the negative 2y, the second term, I'm going to start at 0 and work my way up. 0, 1, 2, 3, 4. Let's simplify terms. 1 times x to the 4th times negative 2y to the 0. Remember, negative 2y to the 0, that's still going to end up as 1 because it's to the 0 power. When I multiply all that out, I get x to the 4th power. That was easy. For this one, I've got 4 times x to the 3rd power times negative 2y to the 1st power, which would just be negative 2y. I put it in parentheses there because I didn't want it to look like I was subtracting it. These are 3 things that are being multiplied, so I wanted to make sure that that negative 2y, that I remember that that's being multiplied, not subtracted. So negative 2 times 4 gives me negative 8. There's an x to the 3rd power, and there's a y. So notice that one ended up negative. Here, we've got 6 times x squared times negative 2y. Well, when we square the negative 2, we're going to get 4. And when we square the y, we're going to get y squared. So we get 6 times x squared times 4y squared. Well, 6 times 4 is 24, x squared, y squared. And it was positive this time because that negative 2 got squared. Next up, 4 times x times negative 2y to the 3rd power. This 3rd power is going to go to each of those there. So negative 2 to the 3rd power is negative 2 times negative 2 times negative 2, which is negative 8. And then that y also gets the 3rd power. Well, 4 times negative 8 is negative 32. There's an x, and there's a y to the 3rd power. Last up, 1 times x to the 0 power. X to the 0 power is 1. Times negative 2y to the 4th power. This gets a 4, and this gets a 4. So negative 2 to the 4th power. Negative 2 times negative 2 times negative 2 times another negative 2 would give me positive 16 y to the fourth power. 1 times 1 times 16 y to the fourth becomes 16 y to the fourth. Notice that some of these terms are negative. So like this one here is just going to stay negative. This one here, well, that doesn't have a negative. That's going to be positive. This one here is negative. This one here is positive. So my final answer is x to the fourth minus 8x cubed y plus 24 x squared y squared minus 32 xy cubed plus 16 y to the fourth power. Now I'm just checking to see if anything can be combined. If there's anything that can be combined, nope, I don't see anything that can be combined. They don't have those same variables, so I am done there. Okay, for the remaining 6 problems, I have all the work worked out there the exact same way that we've got x to the fourth power, the third power, we've got all the numbers raised to the different powers. So it's same exact thing going on here, but I've got it all worked out there for you. So you can go ahead and pause it, take a look at each one, zoom in on whatever you need to. You can kind of take a look at the numbers there. But this way we don't have to spend as much time on the video. You can pause and look at each individual one there. Same exact strategies, nothing different about these, but you can see that the variable is being raised to different numbers. You can see the actual numbers being raised to different numbers, but you can see in the middle of each line, you can see that there are those coefficients, the numbers that we are using from Pascal's triangle. All right, guys, good luck. Hopefully the homework doesn't take you too long. This should be a little bit quicker than doing it the other way.